So today we're going to begin discussing the process of radioactivity and the concept of radioactive decay. And this is a phenomenon that was discovered in the 19th century or the late 1800s. And people noticed that certain substances would spontaneously emit particles, and the way they were able to detect that this was occurring was because the air would become ionized by these particles as they traveled through it. And then also they used cathode ray tubes. These are basically the early equivalents of TV screens. And when they placed the TV screens, or the CRTs, in proximity to these materials that emitted these substances or these particles, they would find that they would leave bright spots every time one of the particles passed through it. They were able to establish that there were three types of particles that were leaving these different types of materials, and they were named the alpha, the beta, and the gamma particle. And the way that the way the three particles were discovered or identified was by placing a radioactive source in a closed capsule and the radioactive particles were allowed to come out only through this opening. This material is made out of lead so that it would absorb the particles that traveled out in any other direction except out to the right here. So to see if the particles would respond to a magnetic field, they passed the particles through a magnetic field. And the purpose of passing them through a magnetic field, of course, is because positive and negative charges respond differently, and so do neutral charges. So they would be able to separate the particles according to whether they were positive, negative, or neutral. And it turned out that in doing so, they did find that some particles traveled to the left and exited out, some particles traveled to the right, and some particles went straight through the field. So if we use the right-hand rule to think about the force that would be exerted on a positive particle, let's turn this a little bit. So if I use my thumb to represent the direction of the velocity and my fingers to represent the direction of the magnetic field, in this case pointing into the paper, for the right-hand rule that means that any of the positive particles would have a force to the left and the particles would turn towards the left. So that means that these particles that are pointing in the upward direction on the paper are the positive particles, whereas if by contrast I use the left-hand rule and I point my thumb in the direction of the velocity of the particles and point my fingers into the paper to represent the magnetic field, then my palm points downward. And so for using the left-hand rule, that corresponds to negative particles. So this means that we can identify that these positive particles turn to the left, and these were given the name alpha. The negative particles turn to the right, and these were given the name beta. And the last particle was obviously neutral because it wasn't affected at all by the magnetic field. And these were given the name gamma. So in the early portion of the 20th century, people began to investigate these particles a little more closely and began to discern some of the properties of these particles. So let's go ahead and create a graph, or a table I should say, in which we'll identify some of the important properties of these three particles. So we'll identify their characteristics, we'll use the alpha and the alpha particle symbol, the Greek letter alpha, the beta, and use a capital beta, and the gamma particle. Gamma particle looks a little bit like a Y. So the characteristics that we would like to look at are, first of all, the nature of the particle. That is to say, what is the particle actually made of? What type of charge does the particle have? What's the mass of the particle? Who's bigger? The penetrating power means the ability of these particles to move through material, and you'll see that these particles are very different in their ability to penetrate through material. The number of ions per millimeter, and this is for assuming that we have a 2 MeV particle. So if we give each of these particles the same energy, how many ions will they produce? So if you remember at the beginning of the lecture, we talked about the discovery of these particles was partially based on the fact that as they passed through the air, they would ionize the gas and leave charged particles behind. And so the number of these particles left per millimeter of travel is a measure of their ability to ionize the air. We can also list how we detect the particles. Certain particles are detected by some processes a little more easily. Also want to look at the energy, how much energy these particles carry. And lastly, we'll look at the speed. So for the nature of the particles, it turned out that with investigation it was discovered that the alpha particle is actually a helium nucleus. That is to say that it has 2 protons and 2 neutrons. The beta particle, it turned out, was a high-speed electron. And it turned out that the gamma ray is actually not a particle at all, but instead it's a photon of light, a very intense photon of light. So the charge for these, of course, for the helium nucleus, that would be a positive 2. E represents the fundamental charge, the symbol for the fundamental charge. In the case of the beta particle, it's simply the fundamental charge, but it's negative. And for the gamma particle is a photon of light, so of course it has no charge at all. For the mass, the alpha particle is quite massive as particles go. So that's 6.64 times 10 to the minus 27th. The electron mass, 9.1 times 10 to the minus 31. This, if you plug these into your calculator, divides 6.64 times 10 to the minus 27 by 9.1 times 10 to the minus 31st, you'll find that there's approximately a 8,000 time difference in their mass. Alpha particle is much, much more massive than the beta particle. And of course the gamma ray is a photon of light, so it has no mass at all. So for the penetrating power, the alpha particle actually has a very low penetrating power. You can stop these particles by only using a few centimeters of air. They don't penetrate materials very well. Solid materials, in fact a piece of paper, would typically stop these particles with little difficulty. The beta particle has a little better ability to penetrate through materials. It would require a few millimeters of metal to stop the particles completely. And finally, for the gamma ray, these have very high ability to penetrate materials, and it requires many centimeters of lead, not just any metal, but a very dense metal. Now, where their penetrating properties go from low to medium to high as we move from alpha, beta to gamma, the ions per millimeter actually goes in the exact opposite way. So you would find that on average for a 2 mega electron volt particle, you would get approximately 10,000 ions per millimeter. Whereas for the beta particle, we only get about 100 ions per millimeter. And for the gamma particles, we only get about 1 ion pair for each millimeter of travel of the particle. When we detect these particles, we find that the alpha particle has a very strong fluorescence. So the fluorescence that we're talking about is when the particles strike the cathode ray tube, essentially the TV screen. They leave a very bright mark, whereas for the beta particle, they cause fluorescence. It's not quite as strong. Fluorescence. And then for the gamma ray particle, they do cause fluorescence, but it's much weaker. In addition, another way that we can detect all of the particles, and they're relatively equal in this respect, is photographic film. All three particles are relatively easy to detect by using photographic film. Now for the energy, we're not concerned with how much energy that these release, but instead we're really more concerned with whether the energies come in discrete levels or whether they're continuous, meaning that they could come with any number of possible ranges instead of specific. So it turns out that for the energy of the alpha particle, these are specific energies, or another word for that, of course, would be discrete. The beta particles are very different, though. They have a range of energies. That range is continuous. So these are not discrete. And then when we look at the gamma particle, we find that once again we get very specific energy levels. Or discrete. In terms of the speed, the alpha particle turns out to be very slow. It has a speed that is approximately equal to only 6% of the speed of light. The beta particle is fast with a speed which is approximately 98% of the speed of light. And of course the photon is very fast because it travels at exactly the speed of light.